Thank you very much. Good morning, sort of, everybody. It's wonderful to be here. Thank you to all the organizers for having me, letting me talk about this continuous tensor networks for lattice models. Now, just seeing this title, right, you may wonder a few basic things. Some certain basic questions might pop into your head, such as what? So I will talk about what. Then after we've done this, you should automatically start wondering collectively how. So then I'll talk about how. And finally, also why, which is maybe the most important question of all. And if we have any time left after this, because for sure I will not explain everything perfectly, then there is huh. Okay. So that's the silly stuff. From here on, it's all very dry. So what? Right. So the idea is to look at quantum lattice models, starting from your partition function. So, right. So this kind of a thing can be expressed as a tensor network. I will go into a bit more detail about how later, but you can sort of intuitively see that this would be a tensor network with d discrete dimensions and one continuous dimension parameterized by beta. Contracting this tensor network is kind of the basic thing that we do if we're doing any kind of a tensor network analysis. You know. And typically we do this by finding a fixed point of the transfer matrix of this object. Now, typically we tend to be very biased, and we contract in the direction parallel to the discrete spatial directions. So if this is time, we contract like this. And therefore we have wonderful MPS tensor network ansatzes that we use, MPS, PEPS, MERA, any of these things, all very much discrete. And the goal here of me today is to try something else. Let's see what happens if we contract from any of the other directions and see if this is any good. And of course, this ansatz that we will have to come up with to do exactly the same thing that we've done before will have to be continuous in some regard, at least in this one direction. Hence, continuous tensor networks. Cool. So in 1D, 1 plus 1D, I should say, yeah, we have such a kind of representation that we can make of the partition function. The basic thing that we have is this square lattice tensor network. I mean, very vaguely speaking, of course, where this MPO here is this thing. It's essentially an infinitesimal complex time evolution of your Hamiltonian. I've taken the liberty to indicate red as the sort of physical direction and blue as the virtual one. Right? And so we have a continuum limit. So this will be relevant later, of course, where, of course, our tensor network is completely discrete, but it is parameterized with this d tau in there. And the continuum is recovered as we take d tau to 0 and we lift this MPO to this specific power, beta over d tau. It has to be exactly this. And only then can you really see this kind of exponential behavior in beta. So what we're going to do is the thing that we always do. You find an MPS fixed point, but in the other direction. So very natural, very reasonable. But here, since the MPO has a d tau dependence, the MPS better also have the appropriate d tau dependence. So what we should see, to be able to do exactly this thing, where we take our transfer matrix, or our triple layer, or our double layer transfer matrix, if we lift it to this power beta over d tau, we should get something independent of d tau and meaningful. This essentially means that we're forced to have this kind of a d tau dependence. Right? Everyone good with this? Basic kind of thing. Indeed, and then this will allow us to meaningfully take this d tau to 0 and really consistently work in the continuum limit. To make this a bit more precise or work with some sort of an example, let's look at a very simple Hamiltonian. So you just have an on-side term, a two-side term, kind of simple. The MPO that you would make for this thing, that I would suggest making for this thing, would be parameterized as follows. The virtual space, the blue leg, has this direct sum decomposition, denoted with a 0 and a 1. This 1 may be of whatever dimension. 0 is one-dimensional. Right, so even though it's denoted with 0 or indeed 1, 1 could be d-dimensional. 0 definitely is, well, not 0 dimension, but one-dimensional. Bit confusing there. Right, so the on-side term goes in there, the two-side term goes there, and what you will do so this clearly is slightly ambiguous in how you would define this 0, 1 and the 1, 0 block of the MPO. The trick is to, well, you want to split it up symmetrically, certainly with respect to the d tau. So there will be a square root d tau in there and a square root d tau in there. So you split it up symmetrically. The h you can kind of split up however you want. It doesn't really matter. But the d tau is kind of very practical to split it up symmetrically. As you all know, really any Hamiltonian that you can rewrite into an MPO and then use for DMRG or whatever can be used like this. So you take your Hamiltonian, you rewrite as an MPO, and then you essentially have this kind of a construction happening. So this is very generic, and that's the point I want to make. And now that we have our d tau dependence of our MPO blocks, we can derive the required d tau dependence of our MPS. This should be this. So your 0 block should be made up of this 1. Otherwise, we wouldn't have this total 1 there. But could have some sort of a linear d tau multiplied with any kind of matrix. The 1 block should have a square root d tau to match with the square root d tau that we put in there, and again with some sort of an tensor this time. So this thing is a tensor, really properly a 3-leg tensor, because this 1 leg again could be whatever dimension. But this, of course, as may not be super clear from this talk this morning, but this is actually a CMPS. Yeah, that's how you would parameterize it. That's why I was wondering about the square root. So this parameterization, I'm not the first to use it. I'm also not the first to realize that there's a CMPS edge to this kind of an MPO. So these people use this for finite temperature studies. So that's a very ingenious kind of use of this idea, because then you can take a periodic CMPS and use it as a fixed point of your periodic CMPO. So this thing they called a CMPO. So it's not the best name that they could come up with, because obviously this CMPO is only continuous in one direction. In the other direction, it's very much discrete. So, I mean, I guess I would have given it a different name, but that's the name we're stuck with. You can also do this in 2D. The whole thing is very similar, kind of simple. This time you get a pepo, of course. Again, the virtual legs are in blue, physical leg in red, and you have the 0 and the 1 space. Everything really just the same. You split the d tau also just up with square roots, symmetrically. And again, whatever Hamiltonian that you can write down in the form of a pepo, which no one does, because no one has any practical use for such a pepo, but certainly it's readily possible to put really any Hamiltonian that you can come up with and put it in a pepo form. Nothing is stopping you from doing this. Yeah, so then you have this. Now, the fixed point should be a PEPS with a d tau dependence. So let's get inspired by what the d tau dependence should be of this PEPS. The MPS had this. So, yeah, okay. The PEPS then should have this, right? Because all that the PEPS is really is just an MPS where the virtual and the physical leg has a tensor product structure. So this thing with zeros everywhere is 1 plus some possibly quite complicated operator Q. And R is just wherever there is everywhere 0 and 1, 1. So there can only be 1, 1, because you have to match up with this pipple. So if you match up with 1, 1 at the pipple, you get this, you get your d tau factor. If there's 2 1s, you get higher orders of d tau, and so all of these will disappear. So this really is the only thing that you need to parameterize this PEPs. But you can do a bit better. Yeah? So one thing is you can realize, and this will become a bit clearer later, this Q and R should be local. So to get the proper scaling of all of your eigenvalues, fixed point equations, yeah, this thing needs to scale linearly in the system size. And so this Q really should be some sort of a, essentially like a two-body Hamiltonian. That's the simplest example you can come up with, acting on this virtual space that I've denoted green here. Right, so your virtual space of this PEPs, a 1D system with Q acting on it. And then R is something connecting this virtual space with a physical leg. That's what it does. Cool, everyone good with this sort of construction? Fairly easy. So in just like with CMPS, you end up just working with the Q's and the R's, so you kind of forget that it ever came in the form of an MPS. The same thing will happen here. You won't be using PEPs in any kind of a meaningful way. You will end up just using Q and R. Right. I suppose it's also clear right now that I am very much of the opposite opinion as the previous speaker. I like to do everything in discretization, so we have completely opposite viewpoints there. But I like this. It gets, because we get to reuse a lot of the tensor network diagrams. Just an opinion. Right, you could do more general things. This Q, all you really need is that this thing is local. So this could be a 3-body operator on the virtual level. That could be long-range interactions. Anything that you can dream up is possibly reasonable to put in there. The same thing with R. Can be arbitrarily complicated, but should be local. The current name for this is not CPEPs, because CPEPs is something completely different. So I've called it one less than C, B. So it's BPEPs and BPEPO. But this is the, it's just one less than C. Yeah, C. Sure, sure. I mean, PEPs is also a boundary thing, but fine. Boundary PEPs. Ah, that's actually pretty good. Yeah, let's say it's for boundary. It's definitely not Bram. So. Okay, so fixed points. How do you calculate them? So this is your transfer matrix, has this kind of very trivial part, and then the meaningful part. So to find fixed points for this thing, you really only need to look at T. Just remembering that your correlation functions are going to be given by exponentials of this T. So if you're looking for the largest magnitude eigenvalue of e to the T, well, then you're actually looking for the largest real eigenvector of T, right? Because complex values, or if it goes negative, it really doesn't do anything. Yep. So yeah, okay, so you expand this thing in orders of d tau. You get your Q from this guy, you get your Q bar over there, and then the R's, both with their square root of d tau, they have to meet each other and form a proper d tau. It's very nice. Same thing happens over here. It's slightly more complicated, but not that much. Yeah, Q on the left, Q on the right, and then R essentially connecting with this half of the Hamiltonian. So you get this kind of a neat way that it all looks. It kind of looks like you have this half-infinite lattice to the left and the right that you compress into this green leg. And then you get an effective dynamics on this sort of compressed space, parameterized by this Q, and then there's interactions with this compressed space and your physically meaningful dimension in the middle. Right? That's sort of a thing that how you could look at it. It's kind of nice. Right, so you call E2, E3 the leading eigenvalues of T2 and T3. From this on, I will assume this. So then your cost function is the leading eigenvalue of this guy divided by the leading eigenvalue of this guy, which if you then expand everything in orders of d tau, this division turns into a minus, right? Because again, you expand everything in orders of d tau. And this thing is the ground state energy, because exactly this MPO, its eigenvalue is supposed to be e to the d tau ground state energy. Cost function? Yeah. Okay. So if you're so let's say you're maximizing the overlap with this MPO. What you would do is you would calculate the leading eigenvalue of this thing, but of course you have to normalize your MPS, so you divide by the leading eigenvalue of this thing. But both these eigenvalues come in the form of 1 plus d tau a number, right? So if you do this division, the actual relevant number proportional to d tau is going to be 1 plus d tau times E3 minus E2. And the number that it should be 1 plus d tau times the ground state energy. Well, minus the ground state energy, because it's e to the minus beta h. Right? So that's how the energy pops in there. So the whole thing looks very much like MPOs, but right, you get energies. It's kind of nice. I'm not going to give any kind of more explanation on how you would do it with BPEPs. It's kind of just the same. But of course, your Q becomes a two-body operator on a 1D system. Q bar the same, and all of these things. Really, the whole thing looks like a Hamiltonian on a ladder, a 2-rung or a 3-rung ladder. So you just use WUMPs or whatever method you desire to contract this thing to find the largest real eigenvalue and MPS eigenvector of this latter Hamiltonian. Quite well. No. But I mean, there is a gauge fixing that you can do to make it Hermitian, but it's not given to be Hermitian. Same as MPS, not guaranteed to be Hermitian. Oh, you could also contract it using CMPS methods, of course, because again, it's just a Hamiltonian, so you can contract it with a discrete method with MPS or again CMPS. So you can go continuous all the way if this is what you desire. And for the purposes of this talk, we all desire.
When you draw those diagrams, that kind of like using the inner product of I, is that like product?
Yeah.
In some sense
Is the 2-norm a meaningful thing to be used in this virtual direction, you mean?
Yeah.
That's a good question.
Like there's no canonical choice.
No, there isn't. And even that's indeed a thing. If you split up the d tau asymmetrically, so not with square roots, then your inner product that you end up having to use to be able to do anything involves d taus. So then your norm matrix would involve square root d tau or d tau to the 1/4, I don't know, whatever. So indeed, there's a certain arbitrariness in there, definitely. It's a good point. It doesn't turn out to be all that bad. I don't know. Yeah. I mean, it's essentially like we always have with like MPOs, and when you're contracting PEPs or whatever, like on the virtual level of PEPs, well, we use 2-norm, but there's no real reason to use 2-norm. It tends to work. It's very practical. Right, gauge fixing. Right, so let's say you want to do right gauge. So always looking at things like this. So this would be the condition that we want. You expand the left-hand side in orders of d tau, also the right-hand side in orders of d tau. The right side has no d tau in there, so this trivially cancels with the 0th order there. And really what you have is that the first order in d tau of this thing should be 0. Cool. You can actually parameterize your Q to have exactly this property, and this is how many of the CMPS optimizations are practically performed. So that's nice. Indeed. A cool thing is that this also works for BPEPs. So PEPs has no gauge fixing possibilities. BPEPs somehow does, because really all you have to do is, right, Q plus Q R plus this R square should be 0, which is very easy to sort of realize for local Hamiltonian type terms. Is it clear to everybody that this is really easy to realize? Okay. Take that as affirmation. Okay, you can also impose hermeticity on this Q and RR, which is practical. Which is essentially the thing that I will be doing always. I found no, I mean, it's super cool that you can gauge fix in a right gauge your something like a PEPS, but there's no practical use that I've found for this. So it's a bit of an open question, maybe nice, I don't know. So how do we optimize? In 1D, we can use very common sort of MPO techniques. The starting point for most things MPO, right, is this kind of zipper equation. It's not a place that most people tend to start, but I mean, it is. Sort of, you can derive CTM from this kind of. Also VUMPs you can derive like this. Right, so if you have this, it's quite clear that you can take this corner and move it all the way to the right, right? Because that's what this is doing. Oop, you move it to the right, and you have a corner over there. Move it to the right, move it to the right, move it to the right. You can also move it down. So this thing really is your left fixed point, and this is your top fixed point. If you have both of them, then this kind of thing should be approximately true. There's some ambiguity in the gauge, of course. So let's say you have the MPS. Easy, just VUMPs or whatever, again, DMRG. Then really the only thing you have to do is look at this thing. This has so this eigenvalue equation, and this will just give you the CMPS. Of course, to solve it, again, you have to expand in orders of d tau. Your 0th order, nice, trivial, because this is left gauge. This is trivially true. Square root d tau, right? Because these things contain square root d tau terms, is trivial. So the half of your Hamiltonian in expectation value, that's your R. And for order d tau, this you use to solve for Q. And now if you pay some attention, you can see that this is essentially the same linear problem that you have to solve in your left environment for VUMPs. Right, so in VUMPs, you essentially have to sum over all the possible positions that your Hamiltonian can sit to the left-hand side. You have to solve a linear problem. This linear problem is exactly this linear problem. So this Q is just your effective left environment that is just output from VUMPs. So once you've run VUMPs, you have this guy. You essentially have Q, then you trivially calculate R, and that's your CMPS. So they're easy to find. But you can also, now that we know this, and we know that we can look at things in this kind of nice continuous manner, we can try to come up with some other technique. So a thing that you can do for MPOs is you can just say, well, if I can do this fixed point equation, I can also do this guy, right? Just the same. You put this guy in the right gauge, take it to the other side. And so you have these two equations that you can just alternate. So you start with a very stupid guess for your MPS, very stupid guess for your CMPS, and you start alternating these things, and you hope to converge, and indeed you do. For MPOs, so this is a known algorithm for MPOs. It's described in this paper. And it's nice. It doesn't outperform VUMPs, so no one really uses it. But it compares quite well in performance. But for Hamiltonians, there is sometimes an advantage. So you will find that VUMPs tends to have, for complicated Hamiltonians or whatever, maybe sometimes they're very simple, but you have these very long tails sometimes, where VUMPs does very well initially, and then it just takes forever to properly converge. And so if you do this alternating algorithm, you somehow don't have trouble with these tails, so you just instantly converge. This is a bit, say again? No, but maybe Yuto knows. No. So these long tails, they were also noticed in this paper and was seen that you can improve over VUMs by just doing something like a gradient optimization. So it is indeed just a weird thing about VUMs. Yeah, I don't know. There's very little research into sort of why VUMs works the way that it works, like this exponential tail, like is there any meaning in this? Because it tends to be really quite robust. Like if you, no matter how you initialize, you always tend to see the same sort of exponential thing going on there. So there might be some meaning to this thing, but I know of no one or nothing that has studied this. So that's cool. So we already have a bit of payoff from looking at these things in a different kind of way. That's the whole point of this, right? We're gonna just do the same thing over again, but looking at it slightly differently, and we hope that we get some payoff. And this is some payoff. Optimization in 2D. Here we make Q and R nice and Hermitian, so that we can do a variational optimization of your double and triple layers. I don't know. Yeah, another thing is your BPEPO is of course always Hermitian in the regular direction because it's an exponentiation of a Hamiltonian. It's sometimes also Hermitian in the spatial direction. Now, if you have this, that's very nice. This makes your life very easy because then you can do a regular old PEPS optimization, BPEPS optimization variationally, right, in this direction. Isn't that sort of clear? So your BPEPO would be Hermitian. So you can just do maximization of the overlap. Right. So your cost function, again, so you have to calculate this E3 and E2, which would be the largest real eigenvalues of your triple and double layer transfer matrices, right, which are these ladder Hamiltonians. So you use VUMs for this. And then you get your energy, or your best estimate for the energy, and that's this thing. And now the cool thing is that if you, okay, so that's what they are, indeed. Now, if we determine these psi's, these MPS fixed points variationally, using VUMs, or indeed just whatever, as long as they are variationally determined, then we get a very cool thing, namely that the gradient of this E2, but also equivalently E3, has this nice cancellation happening. Because this thing, right, the fact that this number should be maximal with respect to, well, this MPS. Right, so this essentially says, okay, this number should be maximal with respect to psi. So this thing just drops away. And this thing also drops away, but it only drops away if T2 is Hermitian. So this is essentially the fixed point equation for VUMs. Right, it's a tangent space thing. You only differentiate with respect to the bar. Oh, sorry, this is VUMs. And if you're Hermitian, then this thing implies this thing. So all of this falls away, and your derivative of E2 becomes this very simple local observable. All you have to do is differentiate Q or R and take the expectation value of this thing. So that's incredibly easy. So your total derivative of your cost function, your ground state energy, is just these two local expectation values, which is really very, very nice. So we get an exact gradient of our approximate cost function. Now this has been, I should make clear, for PEPS research, this is a very, very important thing. We've learned over the years like how to optimize PEPS, and we've done like simple update, full update, gradient optimization with approximate gradients, and we've now, kind of as a community, I think, settled on the best thing is to do gradient optimization with an exact gradient of your approximate cost function. But this is quite challenging to really get because it's not easy to get exact gradients. So we have to do stuff like backwards differentiation, which is complicated to code and costly to run. And this thing is stupidly easy to run, right? You have to contract these two ladder Hamiltonians. Anyone can do this. And then calculate a local observable. So essentially what I'm trying to say is what I'm hoping to achieve with this thing is to redemocratize 2D quantum research. Right? We've gotten to the point where it's become very hard to get into this field. But I'm hoping, because this is so very, very easy, right, that we can make some more progress now, because anyone can do it, right? And a week of implementation will get you this. Cool. Yeah, you can use BFGS because you have an exact gradient, which makes a big difference. That's one of the reasons why we want exact gradients. Right, an example, right? Because we know that we can optimize it now, but how? Right? There's no telling how good this is going to be. So it turns out it's quite good. So this is the Heisenberg model, just 1/2. And you see your bond dimension 2, 3, 4, and your BPEPs, which, so this Q2 is just a 2-body Q and a 1-body R. And you see that the bond dimension 2 BPEPs already outperforms bond dimension 3 PEPs. And this kind of keeps happening. So this is very nice. So at the same bond dimension, you tend to outperform PEPs. Which is very cool, very interesting. I have no idea whether this is systematic or just a happy coincidence. Time will tell. I also wanted to look at the payoff that you would get from making a more complicated BPEPs. And indeed, making a 3-body Q or a 3-body R, or doing both, does give you something, but it tends to be better to just increase the bond dimension. But let's say you're really at the maximum of your hardware capability, maximal bond dimension that you can possibly do on your machine, then you can just start increasing this thing, because there's no actual computational complexity added. Right? Your eigenvalues for AC, they remain the same, and these are essentially your leading complexity thing. Okay. Right, some applications. I'm going very fast. Nice. So you could look at critical phenomena. I have some very, I'm not super happy with these data. So I tried it on the Ising model. Problem is the Ising model is kind of too easy. So if you start increasing bond dimensions, you also see this with PEPs. As you increase the bond dimension, because it is so easy, you get very little back from increasing the bond dimension, and it gets harder to optimize. I don't know why. Maybe it's like a very flat sort of cost function. I don't know. Anyway, it looks like this. So you have your bond dimension 2, your bond dimension 3, which is slightly better. I used a couple of different, played around with some different MPS bond dimensions. So that's why this is happening. All of this is very much still running. So this is preliminary data. But the thing that you want to see, the thing that that was said, like you have this the PEPS scaling hypothesis. This essentially says that the only relevant length scale in your PEPS calculations is the correlation length. There should be 2. There should be the PEPS bond dimension. There should be the MPS bond dimension. In this case, there's 2 MPS bond dimensions. So there's quite a few length scales that could conceivably be involved. But the PEPS scaling hypothesis essentially says there's only one, and it's correlation length. And there's no real basis for this other than that there's a couple of examples where it seems to work. But the prerequisite for this, because it is, I mean, if it's true, it's definitely very useful. The prerequisite for this was that you had to do variationally optimized PEPs. And you really had to converge very well. And so this required you to have exact gradients at fixed bond dimensions. So at the time, very few people, I mean, it was essentially just Uri who was able to do this. And I could do this as well for some 3D code, where you have a similar kind of cancellation happening. And there, indeed, you see that if you do have these things, if you get these exact gradients for your approximate cost functions, so at various finite bond dimensions, you can make all of this data collapse very nicely on top of each other. And so the question was, does it also work for BPEPs? And it seems to work. I did no fit, so this is just with input data, just to see whether it works. It seems to kind of work. Time evolution, that's kind of a cool thing. So this zipper equation for CMPS, again, should be thought of as a thing that is true in 0th order of the tau, and then 1st order of the tau, and square root order of the tau. And each of those should hold true separately. But this also means that you can Wick rotate. Right? You can Wick rotate this d tau. If it's true for d tau, it's also true for I d tau. Right? So you could conceivably do some time evolution. There's only very specific kinds, because this thing really needs to be the ground state MPS, and this really needs to be the CMPS fixed point. So there's this kind of thing that you can imagine, where it does work, right? Because this is the ground state, this is the CMPS ground state, and so you can zipper from the left, you can zipper from the right, and make this kind of a thing, where this is just your ground state MPS, and this is your CMPS. So what this thing is actually parameterizing is time evolution with your CMPS triple layer transfer matrix as a generator, right? Because again, so this transfer matrix is 1 plus d tau, so I d tau, some sort of an operator, and so you evolve. So it's very easy. It's stupidly easy because, right, you get all of these things for free. And it works somewhat. A very simple Hamiltonian, of course. So if you increase the bond dimension of the CMPS, right, it converges. This TBD is converged in DT and chi. So, I mean, the purple and the green is essentially, yeah, the same. Right? So that's nice. The thing is, obviously, the best thing to do for time evolution in 1D is still something like TBD, TDVP, any of this stuff, because you can grow the bond dimension dynamically. You can spread some entanglement. This thing has no ability to spread any kind of entanglement. It all has to be contained in this one site. So it's not going to be very good. But it generalizes. You can do the same thing in 2D. Now, I haven't done it in 2D, but there's really no reason to think that it wouldn't work. All you need is your BPEPs, and then you can do this kind of a quench in 2D, which, yes, 5. Very good. Thank you very much. So yeah, certainly for like time evolution in 2D, there's very little happening, and this would be a very cool thing if it worked. Especially, like, another thing is that like entanglement would spread in 1D really immediately into the thing that you have no access to, right? You fix it to this one side, and entanglement cannot go to the sides. If you're in 2D, entanglement will go in two directions. One direction where it really cannot go. It immediately bumps into your BPEPs. But then in this other direction, it can spread. So I kind of expect this thing to work better in 2D than it works in 1D. And it works quite well in 1D. Another thing is interfaces, edges, strips. All of these are things that really aren't studied much with PEPs, because it's cumbersome, complicated to implement such things. You can, of course, do it. But with BPEPs, you kind of get it for free. Right? Because you can just imagine coming in from the side with your BPEPs, and then you reach an interface or an edge, and then that's just it. You're done. You've calculated whatever it is that you need to calculate. Well, that's what I said. The cool thing is that it gives you an effective Hamiltonian at the edge. So this is your CMPS, or imagine a BPEPs. You've pulled it through this half-infinite line or plane. Up there, you reach the boundary. That's the boundary, BPEPO bit, or CMPO. And then, as I said before, so this thing really should be thought of as like a compressed, effective description of this half-infinite thing. Now, it's going to be a very bad approximation of this half-infinite thing for most excitations. But if you have a localized excitation, a localized edge mode that is also the lowest in energy, then this should be kind of in there. So you check, and indeed for spin 1 Heisenberg, without really trying too hard, you can get this gapless edge mode recovered. So that's nice. So I tried a little bit with the Gitaev honeycomb model, hoping to get chiral edge states. There's no chiral edge states that I found. So you get this thing, which is still a cool thing. So I don't even know if I implemented the right Hamiltonian. I had quite a lot of trouble getting some sanity checks for this thing, so I don't even know if I have the right energy. So I'd be very happy to talk to anybody who could tell me more about what it is that I should be calculating or looking at. But one thing that you can see is that you have your bond dimension 2, 3, 2, 3. This is also 3. So these are still varying quite a bit. But then once you get to 4, 5, 6, they really agree quite well, which is exactly the thing that you would expect, right? And some sort of a stabilization if there actually is such an edge mode over there. I've done the same thing for Heisenberg model. For Heisenberg model, there's no convergence at all. So I'm inclined to expect that there is no edge mode there. Which, who knows? Who knows? Yeah, if anybody has any ideas, I'd be very open to talking about it. This is with the excitation ansatz. So I found so this thing in 2D would be, again, that would be a BPEPS with sort of another BPEPS. This guy, parameterized really just by the BPEPO. BPEPS meets edge BPEPO. And this transfer matrix is just this ladder Hamiltonian. You find a fixed point using MPS. But then you can find excited states with the excitation ansatz of MPS. So you get this momentum automatically as well. It's kind of nice. Yeah. Okay. Other stuff, whatever. There's observables that you might want to look at in imaginary time. It's inaccessible, of course, with PEPs. Very accessible with BPEPs. A thing that I'm very excited about, but I've done no research in, is long-range interactions. So specifically with Miles' talk yesterday, when he said like that it might be possible to disentangle really quite a lot and get really much lower entanglement in your actual state that you have to optimize, only at the cost of getting longer range interactions. So this would be very cool in 2D, where we don't have that much bond dimension to play with, but we really aren't able to do complicated Hamiltonians. But with this, really, there's no reason why you shouldn't be able to do complicated Hamiltonians. Also long-range interaction. All of these things, they kind of get given to you sort of for free. Well, not for free. Because if you can write it as a BPEPO or a PEPO, that's really all you need. Yeah. So the cost would be, so okay, so if let's say your BPEPO, so you have your 0 level and your 1 level, that's the most trivial case. You can add more levels. So the cost that there would be that I would have to introduce more R's. There would be an R at level 1, at level 2, level 3, level 4. But there's really no complication coming in contracting this thing, right? Because that's sort of the physical dimension of this R gets contracted away. You will end up with more Hamiltonian terms, but that's it. Yes? Uh-huh. Uh-huh. Yes. Mm-hmm. Yeah, so that's the thing that I'm, so like I said, I haven't done anything of more complicated Hamiltonians. All I know is that like if there's, so what I've been, the first step that I would want to take is something like a J1, J2, maybe some power law decaying Heisenberg model. This is what I had in mind. Really this type of thing that you get where you do these mode transformations and you get really very complicated, very arbitrary, ugly looking Hamiltonians. This indeed may be quite hard to put into a PEPO. But I got excited when I heard what Miles said yesterday. I thought, yeah, there may be something there. Yeah. Another thing that I might want to add is, well, I think I said it before, like finite, like strips of finite depth. For this, you just take your BPEPs and you apply layer by layer by layer until you get to the edge, and that's that. You've contracted that tensor network. You can calculate all the things that you want to calculate. You can also do finite size. Then you have to contract not with VUMs, but with DMRG. So even patches really are very stable. Like your derivatives are still nice and exact. So yeah, definitely for this kind of stuff, I would expect BPEPs to be a very practical tool. And that's it. Thank you.